the question is fatigue analysis important? Well, the resounding answer is yes. A large number of failures occur due to fatigue. The Health and Safety Executive in the UK found that 25% of all severe failures were a result of fatigue. Additionally, the Norske Veritas reported that 25% of all serious failures are related to fatigue mechanisms. A significant number of international surveys indicate that the overwhelming majority of fatigue failures occur at welds. And although we may not hear about fatigue failures, this does not mean they do not occur. The reason why we may not hear about these type of fatigue failures is that very often an investigation is required to prove that the failure did occur due to fatigue. On the left, we see a fatigue failure on a pressure vessel. On the right, part of an airplane blew off due to the initiation of fatigue cracks at the windows. Basically, we can distinguish fatigue between high cycle and low cycle fatigue. For a weld assessment conforming to ASME Section 8 Division 2 and EN 13445 codes, there are different relevant failure mechanisms. Low cycle fatigue is described as when damage accumulation due to oscillating stress or strain causes failure at typically less than 7,000 cycles. Ratcheting is a fatigue failure that occurs due to incremental collapse. And finally, high cycle fatigue occurs when a crack initiates, progresses with cyclic loading, and finally results in fracture. This typically occurs for more than 7 to 10,000 cycles. So normally, low cycle fatigue is checked against the SPS value, which is roughly 2 times the yield stress. And high cycle fatigue is checked against the fatigue curve, also known as the SN curve, for the applicable material. So we know that fatigue is governed by cyclic stresses. The graph on the right visualizes this, and we see the mean, maximum, and minimum stress within a cyclic stress. The difference between the maximum and the minimum is the stress range, and this is the value that is used for checking against the fatigue curve of the material. High cycle fatigue depends on peak stresses. This is the governing failure mechanism at notches and welds. The high cycle fatigue is governed by the crack initiation and propagation, and fracture occurs due to unstable crack growth. In order to solve for high cycle fatigue, we need to capture the peak stresses in the model, and these originate at the notches. On the other hand, low cycle fatigue is about accumulation of strain. It is sufficient to capture the structural stresses, which are the linearized membrane and bending stresses, and the peak stresses do not need to be resolved. Now, high cycle fatigue is governed by crack initiation and propagation. This crack initiation occurs under cyclic loading containing a tensile component which causes local yielding resulting in microcracks, although the nominal stress remains below the yield stress, Sy. In ductile materials, additional slip bands are generated in the crystalline structure of the metal, leading to cracks. Brittle materials develop cracks more easily due to the absence of yielding. The crack propagation occurs when there is a stress concentration around the crack tip. Each time the stress becomes tensile, and this is a cyclic stress, the crack tip will grow a very small amount. Crack propagation stops when the value of the stress becomes compressive, so very momentarily, and crack propagation is generally due to tensile stress and grows along the planes perpendicular to the maximum tensile stress. So it's important to note that there is no crack growth when the stress is compressive. And these peak stresses originate at a concentration. The stress concentration factor is a stress intensification factor which accounts for the effect of a local structural discontinuity, or as we know it as a stress concentration, and it affects the strength of the configuration. The stress concentration factor is determined by elastic analysis, analytical approaches, or by means of finite element analysis. So there are different fatigue assessment methods. These are typically classified by the type of used code stresses. Common stress definition used in various pressure vessel and pipe design codes are nominal stress, which is the stress away from the discontinuity, and this can be calculated manually. Second is the structural stress, which is the membrane and bending stress, usually linearized. Third is the notch stress, which is the peak stress at the point of failure. And fourth is the hotspot stress, which is the extrapolated surface stress. Based on the design code, the engineer is allowed to use one or more of these definitions. And every fatigue analysis method is based on the corresponding stress definition. so it is important to note that these stress definitions are not interchangeable. Some stress definitions used by common fatigue codes in the pressure vessel and piping industry are shown in the table below. So for example, we see that the ASME boiler and pressure vessel Section 8 Division 2 code, as well as the British Standard and the EN code, all allow structural stresses and notch stresses, except with caveats for which components is valid for which. The ASME B31 code, for example, only uses the nominal stress for fatigue calculation. Now, I will briefly describe the nominal stress fatigue method, which is generally used in the B31 PI codes. And it's very easy to use as the weld area is not included in the calculation. So the nominal stress is usually defined as F over A, so force over area, or M over Z, which is the bending moment over the second moment of area. This is usually a membrane stress. The basis of this ASME B31 pipe code is Markle's testing of pipes with girth welds, and it relies on the nominal general bending stress in relation to stress intensification factor. Another method is the hotspot fatigue stress method, and it is useful for geometrical singularities. The hotspot stress is an extrapolated stress at the failure site, and the purpose of the extrapolation is to exclude nonlinear singularities. The through-the-wall stress is not captured, and thus, in the case that shear stress dominates, through the wall, the surface stresses are underpredicted. The International Institute for Welding is the only code which utilizes the hotspot stress method. Other codes only refer to it. Other factors that can influence fatigue life are load history and type of stress, can be depending on bending versus membrane, the notch details or the geometric concentrations, which depends on the type of weld, the surface finish, and the quality of weld at the toe. This is related to the level of inspection that is performed, and also the environment, the thickness, the residual welding stresses during welding, and as well as the mean static stress level.